So next we have a panel, and we've titled this panel, Can We Sequester Gigatons of Carbon Using Natural Ocean-Based Mechanisms? I'd like to welcome Paul Morris, Seth John, Carl Page, and our moderator, John Preston, to the stage, and then I'll introduce them and give their bios.
I was thinking about what you can measure from space, and I used to be on a board for Star Wars back in the Reagan days, and I remember at one of the meetings they passed around a photograph, which was a guy reading a newspaper in his backyard, and you could tell from the port wine stain that it was Khrushchev, Gorbachev reading the paper, and you could actually, if I could read Cyrillic, I could have made out the headlines. And later, when I was on the board of Mars, we were looking at satellite data of crops, and we could tell by the color shift if a crop was low in nitrogen, low in water, low in whatever. And of course, Mars buys about 15% of all the world's cocoa beans, and so we were focused on cocoa and some of the other crops. But at any rate, my background is I spend most of my life right now starting companies and working on companies that have significant ability to shift carbon dioxide and make the world better. We also are doing some healthcare companies because we think the healthcare system is also broken. I spent about 30 years at MIT, figuring out what to do with two inventions every day. And we started over 300 companies that today are worth probably a little bit over $500 billion and employ over 300,000 Americans. So, I've been involved in technology transfer for most of my life. I actually share one of the awards that you got. The reason I'm up here is I started looking at, actually in 1989, Maurice Strong came to visit us at MIT, and he was getting ready to chair the Earth Summit in Rio. And he challenged us to, he said, what are you guys doing to help the environment? And it turns out we weren't doing much at all. And so I started working on things, technologies that could change the environment significantly back then. And, today, after creating, several more companies related to the environment, maybe we're avoiding probably about 30 million tons per year of CO2 going into the atmosphere with all the companies that I created. But that, that's a drop in the bucket compared to what we need to do. So about 2 years ago, I got together with the former chief scientist at NASA and an oceanographer, Tony Michaels. Many of you know him. And we wrote an op-ed for the New York Times where we looked at the way nature restores climate. And the way nature restores climate is that when things get too hot, the deserts get larger and the world gets dustier, and the dust flies over the ocean, and it drops iron and other fertilization in the ocean, and the ocean then blooms, and you get production of life, and life, we believe, eventually creates organic carbon that sinks to the deep ocean in many parts of the ocean. And so it then takes carbon dioxide out of the atmosphere, leads to global cooling. We looked at ice core data from all of the ice ages in the recent past and found every one of them was correlated with a high degree of dust in the atmosphere. So you say, okay, well, that's great. Nature will take care of it. However, man has ways of intervening. And people say we shouldn't do geoengineering, but yet we are doing geoengineering. We're doing geoengineering by burning fossil fuels and putting more carbon dioxide in the atmosphere. We're doing geoengineering in China by planting trees around the deserts to avoid dust blowing over the cities or ocean. We're doing geoengineering everywhere by emptying our aquifers to grow plants and to make, Sheikh Zayed wanted to make Abu Dhabi green and spent a lot of money doing exactly that. And so every time we do that, or we plant winter wheat to anchor soil so that we don't get a new Oklahoma dust bowl, every time we do that, we're geoengineering, and we're suppressing the dust that naturally would balance out our climate. So a quick quote from Albert Einstein. He said, "We can't solve today's problems by thinking the way we thought when we created them. We need new thinking." And I think what you're going to hear from our speakers today is indeed, new science-based thinking on how to solve these problems. And in my opinion, ocean iron fertilization is the lowest cost way of sequestering not millions of tons, but billions of tons. And I think I'm more optimistic than some of the numbers that, Alan, that you presented. I think, from Ken Buessler, I think we can get to 20 gigatons. And I think there are ways of documenting how we could do that. And ideally, I think we can get below $2 a ton to sequester it. And I also like the earlier talk about bridging the red and blue, because I have no problem allowing the oil industry to fund it. The royalty paid by Saudi Aramco to the royal family each year is $500 billion. For them to fund ocean iron fertilization is nothing. One of my former students at MIT was the grandson of the founder of Saudi Arabia. I know we have very good contacts there and could try to make that happen. Excuse me. Just one other quick story. Back in 1997, I was asked to advise the White House in preparation for the Kyoto summit, and so I went down to Washington. I had a nice slide deck with me, and the first 4 slides were all on nuclear, where we could have doubled the nuclear capacity within the fence lines of our existing power plants. And I was politely told to move to slide 5. And the reason was 70% of the population was anti-nuclear back then. Today, 70% is pro-nuclear in this country. And right now, my biggest project is actually, we have some new technologies that I think could make that very interesting, but I won't go into that. When I was teaching at MIT and Harvard, I would tell my students that what they can accomplish in life is a function of 4 things. It's how hard they work, how smart they work. And those 2 are obvious. They wouldn't have made it to MIT and Harvard if they didn't have those 2 characteristics. The third one is how much leverage you have on the work you do. And so, for example, Bill Gates is an investor in one of the companies I started. And in a 5-minute phone call, he can do more than I can do in 6 months of hard, smart work in certain areas. And likewise, I could do that for some of my former students. So the fourth one, though, is courage. And I think right now we need the courage globally to address the climate change. And unfortunately, a lot of our actions are limited by the least common denominator, are the weakest link in a chain, are the dumbest people. I don't know how to word that in a politically correct way. But if we're going to let that guide our behavior, it's actually us who are to blame. And I'm working on climate with the sense that I can't count on anyone to help me. I'm going to do it myself or do it with people that share my view.
Thank you, John, for that introduction. Just to give you some introduction to myself, my name is Paul Morris. I'm the project manager for the Exploring Ocean Iron Solutions Group. We are based at the Hole Oceanographic Institute. I've worked in ocean science for about 25 years in various capacities, both academic and international civil service. For those of you who don't know me, it's nice to see some familiar faces and many new faces. So I'm going to hopefully give you some background on the science for ocean iron fertilization and what our group is sort of proposing that we do in order to get to to answer the science questions that we need to be able to get to. So I think, how do we advance slides? So we always say that emissions reductions must be the major component to decarbonizing the economy, or to decarbonizing the way we work. And so this graph you see here, we always put this up first. And business as usual is our current projection of carbon dioxide being released into the atmosphere. And the light gray area is our essentially our decarbonization. This is our non-fossil fuel energy. And you can see as the gray area gets bigger, our emissions go down. But really, we need to get to net zero. And then the negative emissions, removing the legacy carbon out of the atmosphere, is where we really need to get to in order to get climate back to a safe level for future generations. And the oceans can't be off the table for trying to do this. The deep ocean is the biggest reservoir that's accessible on our planet. And it contains, if you were to take all the carbon that's been released into the atmosphere and put it into the deep ocean, it would increase that quantity in the deep ocean by 1 to 2%. So the deep ocean is a really big place. And it's something that should not be off the table for thinking about where we can put it. And can we get it, but the question is, can we get it down there deep? And can we get it down there durably sequestered for long periods of time? That's irrelevant to what we're trying to achieve. Most of the models that have been run these days run out to the end of the century. So we're kind of thinking on the order of about 100 years to really give ourselves enough time to decarbonize. And just to give you some background, I'm going to talk through this figure. It was nice to see a presentation earlier that had lots of science and technical stuff in it. This is one of the few graphs I'll be showing, and this is really the fundamental idea that as carbon dioxide goes up and down in the atmosphere, atmospheric temperatures, global temperatures go up and down as well. And the colder ice ages had lower CO2. And really, this was during dustier times. And the hypothesis is the dust was going into the oceans. It was increasing the productivity. And when you increase the productivity, then you have the potential for carbon to be getting into the deep ocean. And you might be familiar with this quote, "Give me half a tank of iron, and I'll give you the next ice age." And this was said by John Martin at a seminar at the Hole Oceanographic Institute, we otherwise call it HUI, back in 1988. So this is not a new idea. It's been around for a long time. And so the iron hypothesis is there are areas which might be limited in iron in the ocean. Can you fertilize those and essentially make them green and grow? And scientists went out and have done experiments, and they've actually done this before. There's been about 13 ocean iron fertilization experiments from the 90s and early 2000s. And essentially, they put iron into the surface ocean in what we call these high nutrient, low chlorophyll, HNLC parts of the ocean. And they were able to turn the surface ocean green. And it's often, they're making these diatoms, these very pretty sort of little glass box animals, there's these little phytoplankton living in the surface ocean, and they're iron limited. And when you put iron in the ocean, they go green, and they grow and they bloom. And these experiments can be seen, from satellite images, and they can see the ocean patch going green, elevated chlorophyll. And some of the experiments with as little as 1.3 tons of iron being added, and this was in the form of iron sulfate, pretty crude sort of material, they were able to get about 2,000 tons of carbon removed at 100 meters. And so this was essentially showing that the iron hypothesis stood true, and these areas were able to be fertilized by iron. But the real question is how much carbon gets deep? And can we use this natural process, the biological carbon pump, otherwise also known as marine snow? Can we get that carbon from the surface down to the deep? And the key questions really that the previous studies didn't answer is the additionality and the durability of that carbon in the deep ocean. And so we did not really have the studies weren't really long enough. We didn't have the technology at our disposal, the gliders, the drifters, the sort of sampling arrays to really answer those questions. Those studies weren't set up to answer those questions, really. They were really testing the iron hypothesis. But now the question is can we use the iron hypothesis to take that next step to see if we can actually get carbon down deep and for long periods of time, or at least long enough to decarbonize? And we're looking at getting the carbon down to levels on orders of centuries to millennia, down deep enough into the ocean so that it's not reventilated back into the atmosphere. So why is iron such a promising climate solution? And as you've probably already heard today, there's some debate about how much it can reliably sequester. The National Academy's report that came out a few years ago is suggesting up to 4 billion tons of carbon dioxide per year, at least in these HNLC regions. You're going to hear from Seth next, I think, who's going to talk about the low nutrient, low chlorophyll idea. This is another idea of how you might be able to scale this up into areas beyond HNLC regions. And a little iron goes a long way. In these previous experiments, about 1 part of iron was getting about 1,000 parts of carbon from the surface down into the deeper part of the ocean. But in nature, we see this really quite higher, to about 1 to 100,000 in nature. So the question is can we do it more efficiently using artificial techniques? And the cost is probably relatively low. The report National Academy's report suggests less than $50 per ton of carbon dioxide. I've lost my, there we go. Less than $50 a ton per ton of carbon dioxide. And iron is relatively cheap. And it leverages a natural process. Sunlight is essentially a free energy source. And we have experience from these prior experiments. And essentially, we know that this also happens in natural areas as well, through volcanic eruptions, forest fires, island plumes. And these experiments, we're now looking at carbon dioxide units, not carbon units. They removed about 4,000 tons of carbon dioxide in a 1-month ocean iron addition experiment. So what are the science community trying to do? The IPCC said that we needed to have carbon dioxide removal in parallel to emissions reductions. And the oceanographic community have essentially got together and formed this group called EXOS, or Exploring Ocean Iron Solutions. And this is an international consortium of experts that have been brought together to really get to the answers about durability and additionality of carbon removal. And currently we have about 60 members, not quite 40 institutions from about 10 countries. And this is a really not-for-profit program housed at the Hole Oceanographic Institute. And it's all about fostering the partnerships and scientific research and outreach, and trying to bring in public and private partners for funding. And it's about trying to build that sort of consortium to a point where we can get the research in the water to answer the questions we need to be able to answer. And you'll see the faces on the screen here, Ken Bissler, who's the director of the EXOS program, and then our steering committee here as well, some of whom you may know. But we have to take a step back, and there will be possibly risks involved with this. But we need to be able to quantify those risks, put guardrails on those risks. The scientists aren't going to be the ones to say whether we deploy at scale, but we need to be able to provide the information to the decision makers and the policy makers to actually decide whether it's a risk worth taking and what those risks might be. For example, downstream impacts might be a risk where if you're taking nutrients out of one place, they aren't available somewhere else. Deoxygenation down in the deeper part of the water column, where you're getting respiration happening from the carbon, this essential food source that's raining down through the water column. Harmful algal blooms are another risk that you may hear about. The release of other greenhouse gases, even more potent than carbon dioxide. So these are some of the things we're thinking about in order to try and understand and have those guardrails on the work and make sure we're measuring for those as well. And then some other issues that we're also considering, for example, fisheries is a question that often comes up. If you're enhancing the bottom of the food chain, will it increase the fisheries? We don't know. You need long, multi-year studies in order to be able to get to those kind of answers. What's happening in the very deep ocean at the benthos. And then, but there are also many benefits from removing carbon dioxide, reducing ocean acidity, and also limiting the worst impacts of climate change, sea level rise, and all the other things you hear about. So just a little word on cost. Research and science and technology does not come for free. This graph here, you could understand this a little bit from the understanding dynamics is replicate measurements, or replicate experiments, should I say. And then the y-axis is additional parameters, additional measurements that you're making. And currently, for the OIF community, we're down at this bottom left-hand corner. This is from the prior experiments. And we think to do the minimum viable project, this MVP1, it's going to cost on the order of about $26 million to do this first experiment. Now, this would assume that all equipment is bought new. If we were able to leverage groups that already have gliders, for example, bring their equipment in, then this number does go down. So platforms and equipment are about 40% of this cost. Personnel, science teams, about another 40%, and sample and data handling, about 20%. And these costs assume everything is bought new. If you do it a second time, this MVP2, by doing the second experiment, is about another 17 million. So the costs start to go down. And this is doing it in a scientific way. And obviously, if you're looking at full-scale deployment, then these costs are likely to come down significantly more as you start to scale up. And prior to the Exodus Consortium being formed, there was a small community correspondence in Nature that was put together by Ken Bisler, Kilipata Ramakrishna, and Margaret Lynan. And really, they wanted to lay the groundwork and the foundation for ensuring that we do this for the benefit of humans. We establish those clear lines of responsibility, commit to open research and risk assessment, performing that iterative and independent assessments, and also to engage the public. We will not do this without wide public support, or at least the public understanding why we need to do the science. And I just want to really finalize on talking about scientific integrity as really that cornerstone of trust. The conclusions and outcomes that come out of this research must be independent and driven by the data and the results. There can't be any real or perceived interference that the research is being biased by the sources of funding. And this is really true for these initial research phases, especially if it guides us to doing things at bigger scales. And so, Exodus is, we're not selling carbon credits or intellectual property, and we're doing that to try and maintain our scientific independence. And really, you'll see some logos on the bottom here. These are mainly federal and philanthropic and sort of family foundation donations that we're using to keep the program and driving it forward. It does not yet pay for the big field studies. That's what we hope to get to, but we're starting down that pathway. And if you want to find out more, I have some small brochures. I will put those at the back of the room so you can get those on your way out. But this QR code will take you to our website when you can certainly learn more. So with that, I will hand over to the next speaker.
Yeah, so thanks very much, Paul, for the introduction to that. As Paul said, he's really been focusing on these colder, high-latitude oceans where there's already abundant nutrients in the seawater, and we're just looking at increasing the effectiveness of turning those nutrients into biomass. What we've really been focusing on, and some of the work I've been involved in, is looking at the low-latitude warm waters, where, again, you can add iron, but it's a very different scientific mechanism. I do want to sort of, at the risk of starting off by throwing out a wet blanket, I do want to be clear that removal of carbon from the atmosphere, marine MCDR, is a very, very important part of the solution, but it's not a silver bullet. And so in addition to removing carbon through all the things we're talking about today, we need to keep our eye on the ball in terms of decarbonizing the economy as well. There's sort of, these are two negative words here. There's positive ways to look at this as well. This is a really huge opportunity. So here in Texas, us egg-headed scientists can perhaps propose some of the basic scientific approaches that would allow us to remove carbon from the atmosphere. But in order to implement this at the gigaton scale, the companies that can move gigatons worth of material around the Earth are perhaps the energy companies, logistics companies. So there's really an opportunity here as well as some challenges. Why is this still worthwhile? Why is this important? I think everybody has a slightly different way of understanding the importance of addressing climate change. I hang around a lot with geologists, and so I really look to the past to think about this. I'm very aware that the climate on Earth has not been stable over geological history. We swing not only into ice ages, but in the past, when carbon dioxide concentrations have been high, we've swung into these really hothouse climates. Where a place like Texas, which has been very comfortable and lovely over the past day I've been here, would be quite uncomfortable. So it's really important to understand that the Earth is not stable, and we need to work hard in order to maintain the stability which we currently enjoy. So right now, in the middle of the South Pacific Ocean, the waters which overlie Tonga, Fiji, these islands here, have very, very low iron deposition coming into them. It just has to do with the fact that the primary source of iron to the surface oceans is from dust. There's very few deserts in the southern hemisphere. The way the wind patterns blow just don't bring a lot of iron dust deposition to the surface of the South Pacific. But underneath the water, there's this is not this particular volcano here. We haven't yet been able to go down and explore the volcanoes. But there are, right now, these underwater hydrothermal vents on the Tonga-Kermadec Ridge, which probably look something like this, along with the hot water that you see coming up. There's a lot of iron. All of those black particles there are iron sulfide crystals coming up from here. And so because of this, you have coming up into the surface ocean there this source of hot water that's very iron rich. What do you see when you look at that from the surface? What you see is that attributed to this input of iron from below, you have this large bloom of phytoplankton that expands across the region. So this is showing chlorophyll in the surface ocean here, these blooms of the plant life, the photosynthetic life that grows in the surface ocean. So why is it that bringing iron up from below, iron from these underwater volcanoes, would cause a bloom in the surface ocean? We think that this is the process which underlies that, which is that 80% of the gas in the atmosphere is nitrogen gas, but it's totally unreactive. There's another form of nitrogen, ammonia or nitrate, both of these sort of interconvert, that's the bioavailable nitrogen. So that's what you need to feed crops or what you need to feed the algae that grow in the surface ocean. And how does nitrogen gas get turned into ammonia? There's a very specific enzyme which has the job of doing this. That enzyme is called nitrogenase. If you grow alfalfa or legumes, you know that those help fix nitrogen into the soil. It's that same enzyme, nitrogenase, which is taking this atmospheric gas and turning it into bioavailable nitrogen. This enzyme is incredibly iron greedy. Different forms of the iron have, plus or minus a few iron atoms here or there, but they can require up to 50 atoms of iron for every nitrogenase enzyme. And so what we think is happening is that, so what we think is happening is that as you add this iron into the deep ocean, you stimulate the activity of this nitrogenase enzyme. So I am a scientist. I am going to just really nerd out for 2 slides here. What I'm showing you is some incubation experiments here where scientists, Bonnet et al. In this recently published paper, took these fluids from the hydrothermal vents and they mixed small amounts of them into the surface waters. And what did you see? You saw that nitrogenase activity increased. So you saw that increase in nitrogen fixation, the conversion of the atmospheric gas nitrogen into bioavailable nitrogen. NIF-H right there, NIF-H copies, that's the nitrogenase enzyme. So that's really showing that there was an increase in the abundance of that enzyme. Once you added in enough iron atoms for that enzyme to go going, the abundance of that enzyme increased. So here even more, there's delta 15N, that's the nitrogen stable isotope ratio, is what's being shown on the right-hand scale in red. On the left-hand scale in blue, POC is the particulate organic carbon export. So what do we see? We see that when the blue bars are high, the red bars are low. When the blue bars are low, the red bars are high. This is data from sediment traps that were put out in the ocean, little cups that collect what's falling down from the surface ocean. And the way you interpret this is that when the nitrogen isotopes get heavier, those del FN15 values go low, that's a sign that there's more nitrogen fixation. And so what we see is on the left, at these times when you have more nitrogen fixation occurring in the surface water, you have this bloom of phytoplankton, that particulate organic carbon, the algae, the phytoplankton growing in the surface ocean. So you put this together and you can sort of imagine, oh gosh, these animations are not coming out right. You start off with iron in the surface ocean. It stimulates the activity of that nitrogenase that allows you to convert nitrogen gas into bioavailable nitrogen, which eventually leads to these blooms of phytoplankton. The efficiency of this process is very, very high. You can sort of choose some different ways to calculate this number. What I've shown here is sort of an average that might get you 1 atom of iron to 15,000 atoms of carbon. So what does an atom of carbon mean? I was a chemistry undergrad, so I'll tell you it has 6 protons. It might have 6 neutrons, it might have 7 neutrons, might have 8 if it's the radioactive C14. But that's not how most people think about carbon. As an oceanographer, I've started to think about, all right, well, we've lost a bunch of the animations. Phytoplankton down here, these algae that grow in the oceans. That's sort of what I've talked about so far is how you get from iron to phytoplankton in the surface ocean. But there's other ways to think about these atoms of carbon. If you're interested in carbon storage in the deep ocean, then you think of that as adding 1 ton of iron to the surface ocean might give you something like 15,000 tons of additional carbon dioxide storage in the deep ocean. You could think about linking that to an economic market and have an economic motive to bring carbon dioxide out of the atmosphere. But even that's not the whole story, right? So the joke in oceanography is that we look at these people on the upper top hand right here and we refer to them as suspended particulate organic carbon. They're scuba divers, so anything that you do in the oceans, these carbon cycles are all interlinked. And so atoms of carbon are also these ecosystems, which are incredibly important for our Earth's natural systems. They're incredibly economically important in terms of bringing people for tourism, for fishing, for all these sorts of benefits that our ecosystems provide. Down below, I've shown some atoms of carbon in sashimi. So we might think of this as dinner, but of course, this also has so many things behind it. So that's an economic industry, that's fishermen whose livelihoods are being provided for here. And so this process of turning iron into organic carbon really very quickly expands from being just a scientific question into being something which has political, social, ecological dimensions as well. So as we've started about thinking about how to sort of effectuate this, where and how we might go to actually test some of these scientific ideas. There's something very, very special about the South Pacific Ocean. It has the conditions which are really right for this particular mechanism where we're using iron to fix nitrogen and then using that nitrogen in order to bring carbon dioxide out of the atmosphere. Warm waters, the diazotrophs, the organisms that fix nitrogen, really require warm ocean temperatures. It's very quiescent, we say. It has low eddy kinetic energy. It makes it an easy place to work oceanographically. As I talked about earlier, it has this naturally low dust deposition, so it gives you a bigger lever that you could use with dust addition. Low N star. This means there's extra phosphorus around. It means that you have sort of a ready supply of phosphorus that can help to catalyze this, this process here. And it's a natural process. There's already nitrogen fixation occurring here, as we saw with the Tunga Kermadec upwelling plume. But how do we go from this sort of scientific view of things, looking at these physical and biogeochemical parameters in the surface ocean? It's going to be, of course, a process of sort of trying to figure out more first about the science, trying to model and understand how adding iron to the oceans will cause a biological response, what that biological response will be, this sort of bloom of phytoplankton that you might get, understanding how that bloom then catalyzes fisheries in the region, the ecological impacts that it has, what are the timescales of that, and how it catalyzes carbon storage in the deep oceans. And so it's really going to wind up being a project that's not just a science project, but something much broader than that, where you start to have to work in these communities and work with South Pacific nations. I'm really honored to notice that Lord Fahafanua, Speaker of the Parliament in Tonga, is here. He's one of the collaborators we've starting to be interfacing with and working with. South Pacific nations are really incredibly forward-looking in terms of climate solutions. They're also going to be greatly impacted by climate, and so it makes sense. So I think there's a lot of ways in which we can begin to bring together these political aspects of the question, the scientific aspects of the question, and the economic aspects of the question as well to make a positive difference. Thank you.
I think we've heard now enough about ocean iron fertilization, ocean nutrient fertilization, that hopefully you're sold by now on a scientific level. But then there's also a question of how you finance this stuff. At Anthropocene, one thing that we've noticed is that there seems to be this difficult relationship between what you can measure in terms of carbon dioxide removal and what you can scale. And this is something that really worries us a lot, because on the upper left here, you see things like carbon capture and storage, direct air capture. These are wonderful methods if you want to talk to a verification bureau, somebody who's actually going to be able to issue a carbon credit that you're going to be able to then sell, and that you're going to then be able to show your investors, your donors, so it becomes a public relations exercise of saying, yeah, our company is involved in capturing carbon. We can show it. We can measure it. Here it is. You can touch it. You can take a picture of it. It's direct. But as you start to get into other methods of carbon dioxide removal, you get to things like afforestation that become more difficult. It becomes more difficult to measure the actual impact of where you are, but they do tend to scale more. So you can get more carbon, but if you're trying to finance this through carbon dioxide removal credits, now you have a problem, because now the verification bureaus, now the people that are actually going to be paying for this, have a more difficult climb because they don't have the carbon. You can't take a picture of it. When you get all the way to the right of this chart, you get to mechanisms that use marine photosynthesis. This is brilliant because you're using free solar energy to produce kelp or sargassum seaweed, which are wildly productive macro seaweeds. They just grow like gangbusters. They absorb a lot of carbon dioxide, but that carbon dioxide ends up somewhere in the middle of the ocean, and it becomes much more difficult to measure it. With ocean fertilization, like we've been hearing about, now you really have a technology that you could scale to gigaton scale quite quickly. That doesn't cost a lot of money, but measurement really now becomes your major problem, in that these are invisible processes that are happening hundreds or thousands of meters below the ocean surface. And so if you want to actually get to the carbon accounting stuff, you have to do things like what Paul's group at Woods Hole is doing, which is these very sophisticated, expensive, slow, cumbersome ways of measuring the carbon dioxide removal. So you can issue a credit against it. So I think, you have the marine photosynthesis zone, or the expensive but measurable zone, and this ends up being a trap. Because what happens right now, if you're trying to finance a carbon dioxide removal project, the reality today is that you need to go to what's called the voluntary carbon market, which is, it's a misnomer. It's not really a market. Nobody's buying and selling there. What it is a dressed up way for companies that are interested in these problems, that are concerned about climate change, to donate money for these kinds of solutions. But you end up with companies donating money for things that don't scale, right? And that won't scale. Because things like direct air capture, we're talking thousands of dollars sometimes, or high hundreds of dollars per ton of carbon dioxide removed. If you go through the math, you're very quickly talking about trillions or tens of trillions of dollars. It's gobbledygook. It's just not a realistic way to get to gigaton scale. But because they are scalable, it turns out that they're financeable. And so some of us were at Ocean Visions in Vancouver a few weeks ago, and to me, it was so exciting to see all these young researchers there, ocean scientists, people who brought all this activist energy to this field, but a lot of them ended up going to where the money is, because you gotta pay your rent, right? You have to pay your bills, and so you have to get to solutions that are financeable. And those solutions are going to be on the upper left of this diagram. And the solutions that might scale are on the other side, where they're not measurable, so they're worth financing, but they're not financeable right now. So this is why I think about this as the carbon dioxide removal trap. Now the question is, how do we get out of this trap? How do we get these solutions that are actual solutions and that are not greenwashing, and how do we finance them? And I don't know the answer to that question. If I did, I'd be much happier. But I have some intuitions about what that answer might be, and Seth spoiled them a little bit because they're about fish, ultimately. What you can finance, the one way that you can get an actual stream of dollars that is not a stream of donations, that is not greenwashing, that is not a solution for a corporate sustainability department, but it's an actual cash flow from somebody who needs to make a payroll at the end of the month, is to go to fishing communities, fishing companies, to go to people who make a living in the sea and tell them, look, when we fertilize the ocean, we're fertilizing the ocean food web. So we're fertilizing, what we're really growing is the food that feeds the organisms that feed the fish, that feed you. So I'm not sure if this is actually going to turn out to be a viable way of financing CDR, but I think it's a mechanism that we need to explore much more actively, because, look, in the end, if in the year 1710 you had a crackpot plan to raise the temperature of the planet, and you wanted to do that by increasing the amount of carbon dioxide in the ocean, you were not going to be able to achieve that by selling carbon credits for burning stuff, right? The way you were going to do that was by inventing a steam engine. You were going to create a mechanism that gave people something good that would also have the outcome that you wanted to have. And then you were going to make that product so compelling that people would buy it, not for carbon purposes, but because they needed it. Well, we need fish. People all around the world eat fish. There's over 1.5 billion people on this planet who rely on fish for more than 15% of their protein intake, right? So given that fishing is a giant global industry and that fish eat the organisms that eat phytoplankton, I think this is something that will end up turning out to be the way to open this field to break the CDR trap. But I could be wrong.
Well, why don't you guys come on up here? We're going to take a few questions from the audience. And by the way, I loved the presentations. You guys did a great job, so thank you. I'll see if anyone, yeah, we have a hand in the back, please.
Yeah, I'd just like to mention that for macroalgae, for kelp, there are economic returns for growing it, and I'll be talking about some of that tomorrow at 1:30. I have a presentation on from the Climate Foundation about what they've been doing.
That's great, thank you. And we have a question here in the middle.
Yes, you're experiencing right now the commercialization of space, okay? You watched it, you lived through it. How do you think the commercialization of oceanography, because you're also experiencing this, although you might not know it, but Noah and the others are checking out, if you've read the papers. So how about the commercialization of oceanography,
Yeah,
in your opinion?
Maybe
Thank
I think Quico, I might want you to take some of this, but one of the interesting experiments that we can do right now would be to look at fisheries that are downstream from the Tonga Vent and see if we can quantify the difference in yield on the islands that are downstream from the Tonga Vent versus those that are not downstream from that. But I thought Kiko's comments about looking at fisheries was a really good one. I also think because the islands are dependent on tourism, that looking at the acidity of the water relative to the coral reef health, where again you could look downstream from the Tonga Vent versus non-downstream. But you're raising a point. The oceans are 70% of the planet, and we've barely scratched the surface. And so there is a revolution going on. At the same time, there's probably a reduction in the federal budget for that revolution. But I think Kiko's point about it being commercially driven was right on target.
This one works. Very quickly about this. Obviously the Tonga Vent is huge in this regard. Not too long ago, I was at this conference, this World Oceans Summit in Tokyo, where I happened to meet the commander of Tonga's Navy and started to have a conversation about the Tonga Kermadec Ridge. And I see this man's eyes just like go wide, and he just had this like epiphany, this moment of, oh, now I understand. You understand what? I asked. He looked at me and said, well, when we did our training back in the 1990s, the oceanographers all told us that if we were patrolling for illegal fishing, we should be looking at the north of our exclusive economic zone, because that's a convergence zone, that's where the nutrients are, that's where the fish are likely to be. But we keep finding illegal fishing vessels from the Philippines and from China in the south of the EEZ, and we didn't know why. Nobody had explained to us why. And so we go and we look at the maps, it's like, oh, this is what's happening. The fertilization is happening in the south of the Tonga EEZ, and so there is a fishing boom. And this man looks at me, it's like, he kind of smiles and he tells me, so I guess the fish heard about it first, and then the illegal fishermen heard about it second, and then the scientists heard about it third, and then we are hearing about it last. I think that is proof of concept right there, that there is a commercially viable way of financing this stuff. Just looking at fisheries, hopefully legal ones in the future.
So maybe Seth or Paul, would you like to comment on that question? Sure. Try yours first.
I'll try. Oh yeah, I think I'm live. Yeah, I think just back to this point about atoms of carbon. They sort of, atoms of carbon are all carbon, but they have very, very different sort of values, not just economically, but sort of spiritually, ecologically. But certainly the value of a ton of carbon in fish is much more than it is for phytoplankton. My wife's in the film business, and they often talk about one for me, one for the studios, or one for the money and one for the art. And you can sort of imagine the same thing with carbon atoms, that a ton for the fish, and that's where the economic value is, and then 99% of those phytoplankton go uneaten and wind up in the deep ocean and could make a real difference in terms of long-term carbon storage.
Yeah, this is working too. So the selling it on fisheries is, I think it has been done before, and things didn't go as planned. I think if you're going to do that again this time, it needs to be done in a very careful way with the right science that sort of, studies the fisheries before you go and do that kind of stuff. So you actually have a good baseline. I was talking to somebody who does fishing up in the Pacific Northeast, up in off Alaska, and they would want to see at least a year of study before any experiments were deployed, so that they have that baseline and they can see a response. Doing fishery studies is a multi-year process. And if that doesn't deliver, then I think that could be, you could end up in a big problem, and it could be then off the table again. So I think it has to be done in a very careful, well-controlled way if you want to sell it on that premise.
Yeah, we totally agree. This everything needs to be scientifically rigorous. But the nice thing about the Tonga event is that nature's doing that one and has been doing it, and so you can take advantage of some of the things that nature is doing. But I totally agree, Paul, with your point. Any other questions? Peter, you have a question here. You can borrow this.
Yeah, Quico, your economic model is interesting. I'd looked at that for several years. But the issue is the economic incentive is to get more fish. And as Seth pointed out, that they end up on the table, digested, turned back into CO2. And so it doesn't lead to reducing atmospheric CO2. I'm wondering how you see that working, because I just don't see it.
A small measurement of what's really going on. And so, yeah.
Look, the way I see it is that a major problem that this whole field has right now is that it has this sting of it feeling untried. It hasn't been done before. It feels scary. There's a big G word, which I will not say, hanging over this field, right? And we need to turn that corner. And one way that we turn that corner is by leaning into the ecological benefits, showing that the unintended consequences are good, right? So right now, people have this sense that the unintended consequences are likely to be things like harmful algal blooms, scary things that we don't want. And that, so if we talk about that second, we put the scary part second, no, that's not the correct tactical way to do it. The tactical way to do it is to lead in with the co-benefits, to say the major co-benefit of increasing primary productivity is more fish, probably, to start there. And then as you begin to turn this into a normal way of the way fishing countries manage their fisheries, and you establish it as something that is not untried, not untested, that's just a normal part of fisheries management, then on the back of that, you can say, hey, you can also issue some carbon credits against this. And now it's not controversial anymore. Now it's just become a normal way of the way you manage the oceans. And then in 5-10 years, you can move to these more aggressive, more carbon dioxide removal centered approaches. And by that time, trying to mobilize opposition to it is going to be impossible.
Let me just elaborate a little bit, because the fisheries is an indirect measurement of the carbon production, and as Paul mentioned, about 99, maybe even 99% of the phytoplankton that you generate are sinking to the bottom, are sinking on their own and not being converted to fish or to organic carbon. But it gives you a really nice indirect measurement of what's going on. And it has an economic benefit, which is where Quico is coming from. Do you guys want to add anything on that, or should we go for another question?
I can do a quick follow-on, which is useful.
Yeah, right behind.
Here we go. Yeah. So with our orbiting carbon observatory data, what we found is any place where fisheries are working, the orbiting carbon observatory reported essentially zero removal of CO2. That as much carbon, as you were saying, John, as much carbon is produced, the fish eat it all. And it was only in the downwelling eddies that we could see negative, the removal, where the eddy will pull the carbon down before the fish have a chance to metabolize it.
Probably we shouldn't debate that issue because you could go both ways on the eddies. Going up, you're spreading the iron over a larger area. Going down, you're sequestering the carbon. There are counteracting effects on both approaches. And I think the scientific studies need to give us the data to answer those questions rather than to have a debate in this environment before we have the data.
Well, this is the data. This is based on data. It's just I don't have any money to publish it. So I don't know if the scientific community is interested, but we have the NASA data.
Of course, we should have all the data. Any additional comments on that, or should we take another question? Okay, we got another question coming from...
Hey, my name is Tito Jankowski. I'm the CEO of Air Miners. We're an ecosystem and community and a well-known startup accelerator for carbon removal. One of the things I've seen was we had a team that was talking about doing ocean alkalinity enhancement, and they ran into, okay, this is going to take permitting, and there's going to be a lot of work for us to start doing that experiment. And so one of the creative things they did was they said, actually, can we use? Are there other bodies of water where we could do this work? And they ended up working in pit lakes, which are when you abandon a mine, it fills up with water, and then they're able to do these experiments in areas that don't have the same concerns or the same permitting and regulation. I'm curious for the panel, do you see any opportunities to in terms of getting things started, to do experiments in smaller bodies of water or lakes or other places like that, or even artificial lakes? I don't even, just kind of curious about what you're seeing there. Thank you.
Maybe Seth and Paul, you guys could take that question. You want to start, Paul?
Okay. So for the HNLC, the high nutrient, low chlorophyll areas I was talking about, these tend to be away from the land masses. As you get closer to land, you get closer to the iron sources. So it needs to be in these iron-depleted waters. They happen out at sea, essentially. So trying to find those spaces sort of closer in is not really an option.
Yeah, I do think you maybe have to be in the oceans, but I do think there are ways that you are going to want to be very careful about how you design these experiments to sort of work up slowly and really be able to fully understand the impacts. One of the sort of useful things about iron chemistry is the reason why there's no iron in the surface ocean is it's very insoluble. And so with all of these experiments, if you were to add iron, you're looking for this sort of response over the course of maybe a week or several weeks. But after that, the iron will just very naturally coagulate out and drop to the bottom of the ocean. So one of the things that's very useful about this technique is we can try it on small scales, probably in the oceans, not in lakes, but in various different parts of the oceans, and know that if we're not getting the results we expected, if there are negative outcomes, then we can stop adding the iron and we'll very quickly revert to the prior conditions.
We have time for one or two more. It was one way in the back.
Just a quick comment on the, somebody said the phytoplankton are sinking to the bottom of the sea. That's not what's happening. Fecal pellets are sinking to the bottom of the sea. So the whole life of a fish, it's processing carbon and putting it to the bottom of the sea, and we only consume it at the end. But its whole lifetime, it's been processing carbon and sending it deep in the ocean. So it's, what is it, maybe 1% or something? So I think you're sequestering a lot of carbon when you have a lot of fish.
Yeah, that's a great point. Thanks for bringing that up. We have another question way up here, but this is we won't even answer the last question just so we can hear this one, and then we're done. Okay, because we only have 2 minutes left.
Thank you. Have you looked at hydrothermal carbonization of the macroalgae? Because that would have another purpose as well as cleaning the beaches or where it will end up, and there's a huge economic impact on that.
Would one of you like to take that?
And you could also measure it.
Okay.
Hydrothermal carbonization, you compress it under high temperature, and you end up with a biochar-like product. It doesn't need to be dried out, and you could take all that sargassum and convert it into measurable carbon that you could just dump in the ocean. Or you can use it for fertilizer as well.
It's a valid point, and I know the chemistry of doing that. I don't know anyone who is doing it, but I agree with the point. I think at this point we got to wrap it up, and thank you very much, everyone.